problems with distributed loads. We did, so before the test, we did a problem where the distributed load came from the weight. So I'm going to do two types of triangular distributed load problems. Yeah. We're still in the middle of one. The exam was on everything up through structures. The next topic was internal loads, and we're finishing that up. We might finish it today, but there's really only one more thing I need to talk about, but there are two examples I want to do. So back to probably about a week. And in internal loads. Okay, so let's say we have a beam with a pin joint at the middle, and a roller at the right end. And a distributed load. No, let's not do that. That's too much. Let's do this. Distributed load all the way. Let's say that this is 1 meter and this is 1 meter. And let's say at the highest point it's 10,000 newtons per meter. And we want to calculate the internal loads. Let's ignore the weight of the beam on this one.
So what's different in this structures as far as with this structures? Is there a different process?
For structures? Well, this only has one member, so you only have to do one thing. But the key thing here is that we're not just calculating the external loads, which is what you're trying to do with structures, calculate the external loads on each member. On this, we're trying to calculate the tension, shear force, and bending moment. So what's the first thing we have to do? Calculate the external loads first, and we have to do that. We don't need to know the external loads here because our cuts are never going to get that far, but we do need to know it here. Right, so first I'll do a free body diagram of the whole thing. Good job showing up finally, Fred. Yes. And so the pin joint at the middle, that provides a force vector. I'll call that RA. The roller at the end is an upward force I'll call RB. And now that we've chosen a body to isolate, we can think about how to represent that distributed load as a point force. It's a triangular shape with a base of 2 meters and a height of 10,000 newtons per meter. And so the total area, the total force, is 2 times 10,000 divided by 2. And the centroid is 1/3 of the way from the wall side to the point side. So here. This distance is 1/3 of 2 meters, so 2/3 of a meter. And that means this side is 1 1/3, 4/3. Any questions about that free body diagram? Newton's second law says the RA vector plus 0, negative 10,000 plus 0 RB is equal to zeros. And the moment equation, we have to choose an about point. Let's do the one at the center. There's no moment produced by RA because that's at the about point. Then what's the moment arm for the 10,000 Newton force? This distance is 1 meter. This distance is 2/3 of a meter, so this is 1/3 of a meter. So we have 1/3 times 10,000. And is that positive or negative? Negative. Yep, that would, if the hinge is at the red dot, that would make it rotate clockwise. So negative. And then what's the moment arm for RB? 1. Our about point is the middle. So moment arm of 1, the force is RB. And would that make it rotate clockwise or counterclockwise? Counter, so that's plus. All that adds up to 0. So RB is equal to 3333.3 repeating. And that means that RA is equal to 0 for the X, and then for the Y, positive 66666.6 repeating. Okay, so now we have the external loads. Now we have to think about the cuts. Now if you look at this free body diagram here, how many places are there where we have to, how many places are there where those subfunctions can change? There are the 2 endpoints. You always count the endpoints. And then there's this. And then what about this one? That's right. So there's definitely 3, okay? The 2 endpoints and this, those are definitely places the subfunctions change. But this 10,000 is not an actual thing. That's just a mathematical thing that we use for convenience. The only physical things are real point forces and places where those distributed load functions change. So if you look at the real picture, you have 1 there, 1 there, 1 there, and no other points due to that distributed load. You know what I'm talking about? So the answer is 3. N is equal to 3, and that means we have 2 cuts. And the reason I said to look at this one was it's a super easy mistake to make. It's once you've gone through all this, this is the last diagram you have that's tempting to use to figure out, how many cuts you're going to have to make. But if you base the number of cuts on a picture that represents the distributed load as a point force, you're in grave danger, of getting one wrong. That had the distinct feel of all of you just like listening to me talk and being like, what the hell is he talking about? But you understand what I'm talking about? I could see the thought bubbles. You know what I'm talking about? No. Pete's thinking of like a Twix commercial. But yeah, so those points are, the key points are where there are real point forces, point loads, and where the distributed load functions change. And so there's only 3 of those. So n is equal to 3, and that means we have 2 cuts. It is a good commercial. I'll give you that much. The Twix commercial? I don't know. Yeah. Twix. Yeah, those are good. I can't think of. If I did come up with one, it would be from like 30 years ago. I don't even know if they still make Twix.
Remember the one where there was 2 factory tours?
Oh, and yeah, like a cookie factory and a chocolate factory. Here are the candidates for adding 1 to n. The endpoints always, so you always start with 2. And then the other things are points where you have either point loads or places where the distributed load function changes. And then you have 1 less cuts than you had in. So our first cut is
Square on the left side of that beam. Triangle on the other side.
Right. They change, that's right. Or changing from a triangle to 0 is also changing. That's right. Okay, so cut 1 is valid for x's between 0 and 1. And so we're looking at a piece of the beam like this. We're skipping all this. So the black is what we're isolating. Oh, in the set, you haven't seen that before? It just means x is part of this interval between 0 and 1. So x is part in this set is what it means. Okay. So x is somewhere between 0 and 1, and if it has, right, and if it has round brackets like that, it means not including 0 or 1. Yep. And if it has square brackets, it means it is. And we're always doing non-exclusive like that with the round brackets. And so what are we considering and what aren't we? So there's all this part of the distributed load, all that blue part of the distributed load, we're not considering, right? That's not, all of the distributed load over here is not acting on this. And then there's also, no, so we're making, what we're doing is isolating a piece that's representative of any piece going from a small little sliver at the left to going from the left almost all the way to there. Okay, so this is like a general free body diagram that's going to represent a lot of things. And all the blue stuff that I've drawn, we're not worried about that. That's not part of what we're considering right now. And then we have the internal loads, T, V, and M. Okay, well, looking at the picture this way brings up a problem we have. Over here, the distributed load is 10,000 newtons per meter. the length of this piece that we're looking at is x. Well, if we were isolating the whole thing, we know that the height of the distributed load would be 10,000. We're only looking at this part, and the height of this is obviously not 10,000. So we need a way to represent the height of this distributed load at an arbitrary value of x. Okay, so the way to do that is to represent the height of this distributed load as a function of x. You know, the height is this line. And so we need a function, we need the equation for this line. Okay. So the equation for this line, that's what we're going to call Q. And since it's a line, that's going to be mx plus b, where m is the slope and b is the y-intercept.
Y-intercept?
Yeah. Okay, so when x is, let's think about the slope first, and then we'll do the y-intercept. So how do we figure out the slope of this line? Yeah, good. No, you're right the first time. So that line, this is the same line, you know. It rises 10,000 over a distance of 2. So the slope is going to be 10,000 over 2. So we know that it's 10,000 over 2 times x. And now we have to think of what the value of Q is when x is equal to 0. Well, x equals 0 is this point here. And the distributed load is 0 all the way at the left hand. So in this case, the y-intercept is 0. Our Q function is 5,000x. And that means that since the right end of this piece is represented by x, the height here is 5,000x. That's the height of the distributed load at the end of our piece. Any questions about that yet? I'm just doing that for the right side of the piece we're talking about. That's just telling us how high that triangle is. And so now I'm gonna, well, the next thing we have to do is we have to represent that triangular distributed load as a point force, because that's the only way we know how to deal with it. So to do that, I'll draw this triangle. This triangle has a width of x, a height of 5,000x. The centroid is here. And the area of that triangle is x times 5,000x divided by 2. So 2,500x squared. So now I can redraw this free body diagram. I'll look into that. So we have the internal loads T, V, M. And now that triangular distributed load is replaced by a point force with a magnitude of 2,500x squared. And what's the distance? So we know that this whole thing has a length of x. Good. So this distance is 2x over 3, and this is x. Any questions yet? What? Yeah. 2/3 Twix. So Newton's second law says 0, negative 2500 x squared plus t negative v is equal to 0. So t is equal to 0, and v is equal to negative 2500 x squared. And now the moment equation. Like always with these cuts, the about point is the left end point. So what's the moment arm for the 2500 x squared force? Yep. 2/3 x, that's the moment arm, times 2500 Twix squared. Is that positive or negative? In this case, it's negative. Plus m minus vx is equal to 0. So m is equal to positive 1666.6 repeating x to the third plus vx, so that's minus 2500 x to the third, because v is equal to negative 2500 x squared. And so m, if you combine those two terms, is minus 833.3 repeating x cubed. And last time I gave you those checks, right? The 6 checks. Okay. Well, we can do the derivative checks now. dm dx is negative 2500 x squared. So dm dx is equal to v. So that one works. Negative dv dx has to be equal to q, the function that represents the distributed load. dv dx is negative 5000x. Negative dv dx is positive 5000x. And looky here. If q of x isn't 5000x, yeah, it works every time like that. Any questions about that? Okay, cut 2. So these internal loads are all valid on the interval x between 0 and 1. Yep. Okay, so now cut 2. Now we're dealing with x values on the second half of the beam. So x is between 1 and 2. Now our general free body diagram, the right end goes somewhere past that midpoint. So we're isolating the black piece. We're not worried about the blue piece. The distributed load. Oh no, my angle was off. Okay. This time, the part that we're isolating has that distributed load, like it did before. Now it also has that force at the midpoint. That was, yeah, 6,666 pointing up. So I'll put that here, 6,666.6 repeating. And it has the internal loads, T, V, M. We didn't get out to this. And we have the same thing going on as before. The value of the distributed load is 10,000 at the end of the blue, but we're not interested in the blue. So we need an equation for that line, and it's going to be the same one it was before. This function Q representing that line is 5,000x. I guess I'll do this again. So this triangle has a width of x, a height of 5,000x. The centroid is a third of the way from the wall towards the point. The area is base times height over 2. And now we can represent this free body diagram with a point force instead of a distributed load. So we have the upward force of 6,666.6 repeating. We have the downward force of 2,500x squared. And we have the internal loads T, V, and M. Okay, the distance between the end and the 2,500x squared force is 2x over 3. What's the distance between the left end and the 6,666 force? Yep, that's right. That's just a fixed distance apart. It doesn't, where the right end is doesn't have any effect on the distance between the left end and that, and where that joint is. So this is just 1. And the whole thing, the whole piece that we're isolating has a length of x. So Newton's second law says 0, negative 2,500x squared plus 0, 6,666.6 repeating plus t negative v is equal to zeros. So t is equal to 0. V is equal to negative 2,500 x squared plus 6,666.6 repeating. And then the moment equation, the moment arm for that 2,500x squared force is 2x over 3. Is that positive or negative? The 2,500x squared, the moment? Negative, yep. What about the 6666? That's positive, and its moment arm is 1. And then we have plus m minus Vx is equal to 0. So m is equal to positive 1666.6 repeating x cubed minus 6666.6 repeating plus Vx and now substitute V in. M is equal to 1666.6 repeating x cubed minus 6666.6 repeating minus 2500 x cubed plus 6666.6 repeating x. You can combine the two cube terms and you get m is equal to negative 833.3 repeating x cubed plus 6666.6 repeating x minus 6666.6 repeating. Imagine how funny it would have been if I would have said all those sixes as Twixes. Damn it. Yeah, that's true. Next time. Okay, so this is valid on the interval from 1 to 2. We can do those derivative checks. dm dx is negative 2500 x squared plus 6666 point Twix repeating. And that's equal to v. And then dv dx is negative 5000x. Negative dv dx is positive 5000x. And that's q. So those derivative checks work. One other thing to notice is we had a jump in the shear force that had exactly the same magnitude as the vertical point force that occurred there. So if you have a horizontal point force causes a jump of that same magnitude in the tension, and a vertical point force causes a jump of that same magnitude in the shear force. Let's plot these. Yeah, so there was no tension in this problem, but if somewhere inside the beam you have an external point force, okay, whatever its horizontal component is, at that point the internal tension jumps by that amount. Yeah, it does. And if in the vertical component of that point force is the magnitude of the jump in the shear force, same way, B. Yep. All right, so let's calculate these. Well, T is easy. That was just 0 the whole way. Shear force. So we had negative 2500x squared. So it goes from So it goes from 0 to negative 2,500 at the midpoint. And then jumps up to here and draws, I think it must look something like that. Well, I know the concavity, and I know the slopes, and I know the values at the different places. Yeah, I don't know exactly. Yeah, I don't know. I'd say definitely not the scale, and possibly not accurate in any way, but I do know the concavity. And then the M, holy moly, why did I start this? So what did we have up here? Cubic function. This one, I think is going to look like, I think it's going to look like that. That's my guess. Go home and check on your own. You don't pay me to draw graphs. Oh yeah, that's true. Yeah, that is. Any questions about that? Okay, so that's just the basic idea of calculating the internal loads with distributed loads. So now there's one more that's more of a nuisance than that, and I'm going to go through that example. And it's a little surprising. What? Oh, those graphs? Yeah, I was going to like interpret them, but now I don't know if they're right or not. I'm not going to talk about those. I think there's a 40% chance that B is actually what it looks like. Feel a little better about M, but anyways, the idea is if you're trying to figure out where you're worried about this beam breaking, you could look at these values and say, well, it doesn't favor anything. V, the absolute value of the shear force, appears to be the biggest all the way at the right end, or maybe it's biggest close to the midpoint. The bending moment appears to be biggest close to the midpoint, and so we're probably most concerned about this thing breaking near the midpoint. That's how you would use that. Okay, so the last example I'm going to do. Sure.
That one in the middle?
Yeah.
So it had a decrease?
It had,
At the midpoint?
it had a jump of, yeah, of positive 6666.6 repeating.
You had the negative. You had the
Oh.
force down and then you had the force shortly after.
So yeah, there was that force in the middle that made it jump. I made it jump 666, but it actually jumps 6,066. So maybe something like that. Okay, let's stop talking about those graphs. Okay, so this time, the beam, it's a cantilever beam connected at the right. So far, so good. You know, when the only external loads, or the only unknown external loads are at the right, you can skip calculating the external load, so that's great. And then we have a triangular distributed load like that. No, that is not going to end up being great. So this is 5,000 newtons per meter, and let's say this is 3 meters long. What's N for this? Yep, just 2 endpoints. The distributed load never changes. There are no point loads. So N equals 2. That means all we need is 1 cut. That's good news. But let's look at that cut, and it's going to be a real downer. So cut 1 is valid for x's between 0 and 3. That's the piece we're isolating. Here's the piece we don't care about. We know that over here, the value of that distributed load is 5,000. That's more good news, you know. We know the height of that there. But the problem is over on the other side. Because that triangular distributed load was facing the opposite way, when we make our cut, no matter where we cut it, we chop off the part that gives this thing its identity as a triangle, you know? So it goes from being a triangle that's easy to deal with to being a trapezoid that's a pain. Does that make sense?
Yeah.
Okay.
Yeah. Couldn't you just break it into a rectangle and a triangle?
That's what we're going to do, yep. It's still going to be a pain, but yes, that's exactly what we're going to do. Yep. So, here's our shape. We'll break it up like that. We know that this width is x. We know that the whole height here is 5,000. But we don't know the height of the triangle yet, and we don't know the height of the rectangle. And we need both of those in order to calculate the point forces corresponding to these distributed loads. Yeah, so if we can calculate that function that represents this line, then that tells us the height at this point, x. And that's the height of the rectangle. Okay, so that q is going to be the height of the rectangle. What is that q? So this time, the rise is negative 5,000. Now it goes from 5,000 to 0 over a run of 3 meters. So q of x is equal to mx plus b, which is negative 1666.6 repeating x. And what about b? When x is equal to 0, what's the value of the function? 5,000. Because, you know, the left end is x equals 0. And at x equals 0, the height of the distributed load is 5,000. So this function q is negative 1666 x plus 5,000. And that means that the height of this rectangle is negative 1666.6 repeating x plus 5,000. Now we can use that to calculate the height of the triangle. What's the height of the triangle? Right. Exactly. 5,000 minus this. So 5,000 minus quantity negative 1666x plus 5,000 just gives positive 1666.6 repeating times x. And now we can treat these totally separately. We have a triangle with a height of 1666.6 repeating times x and a width of x, and the centroid is a third of the way. The area is 1666.6 repeating x times x divided by 2. So 833.3 repeating x squared. Yeah, so the centroid is just going to be x over 3. No, we don't have to do that. We're just going to treat it as, you could do that, but it's one extra step. You might as well just represent these as two separate point forces, one for the triangle and one for the rectangle. Yep, same answer. Yep. And now we have the rectangle. It has a height of negative 1666.6 repeating x plus 5,000 and a width of x and a centroid right in the middle. And the area. This is the first time that we kind of have to think about signs, because the signs can be sort of confusing with this rectangle. Even though that leading term has a negative on it, if you plug in a value of x between 0 and 3, this thing here is positive. Like if you ever get confused about that, just plug in one of the values in your range, you know, your allowable range of x values. And so the area is just going to be this thing times x. And this is going to get confusing because we're going to have to multiply this thing by, when we start talking about directions, that can get confusing. So the area of this rectangle is x times negative 1666.6 repeating x plus 5,000. And so that's negative 1666.6 repeating x squared plus 5,000x. And now we can represent both distributed loads as point forces. We have the force from the rectangular distributed load. That has a value of negative 1666.6 repeating x squared plus 5,000. And we have the point force representing the triangular distributed load. That has a value of 833.3 repeating x squared. Yes, yep, I just forgot to write that there. And then the internal loads, T, V, and M. And the distances to these things, what's the distance from the left end to where that the point force from the triangular distributed load acts? X over 3, yep. And what's the distance from the left end to where the other one acts? That's x over 2. And then the whole thing has a length of x. So Newton's second law says, so now this is where the signs can get hairy. The way to think of this now is these are both positive values, no matter what x is. Okay? But they're both acting downwards. So you can think of it as taking these numbers and multiplying them by a unit vector pointing down. What's the unit vector pointing down? 0, -1. So this is 833x squared times the vector 0, -1, which gives you 0, -833 x squared. And what's this other one times the unit vector pointing down? Right. Those signs, we have 0, +1666.6 repeating, x squared minus 5,000. X, dang it.
So why do we not say that the piece has weight?
I just did it because it made it more simple. The way that would come up in a real problem is if the forces applied by the weight are much, much smaller than the other forces, then you can ignore the weight and it won't change the answers very much. If you do have the weight, then you have to do that also as a distributed load, as a rectangular distributed load. So, yeah, it doesn't, it just adds more stuff you have to do. It doesn't make it hard or anything. Yeah. So we got this plus t negative v is equal to zeros. So t is equal to 0. V is equal to positive 833.3 repeating x squared minus 5,000x. We can do the derivative check. dv dx is equal to dv.
Yeah, no, I'll be right.
Oh, yeah. Okay. Yes. dv dx is 1666 x minus 5,000. Negative dv dx is negative 1666 x plus 5,000. And that was our Q function. So that one works. And then dm dx, oh, we haven't done that yet. I got so excited. So now the moment. We have a moment arm of x over 3 times a force of 833.3 repeating x squared. And is that positive or negative? Negative, yep. And then a moment arm of x over 2 times a force of negative 1666.6 repeating x squared plus 5,000. Is that positive or negative? Jeez. That's like a serious mental block. Okay. Is that positive or negative? Also negative. And then we have plus m minus vx is equal to 0. So multiply those out, and you get, is that negative 266.6 repeating? X to the third. Plus 833.3 repeating x to the third minus 2500 x squared plus m minus vx is equal to 0. So m is equal to, I guess I'll combine these two right now. And that will be a value of 466? 566? Oh, is it? I don't know. Yeah, can someone just make sure about that? Is it 277.7 repeating? 277.7 repeating. What's 833.3 repeating minus 277.7 repeating? 544? Nope. So that's negative 555.5 repeating x cubed plus vx, so that's plus 833.3 repeating x cubed minus 5,000 x squared, and then combine the x cubed terms, and does that give you back 277? That's 833 minus 555. So 277.7 repeating x cubed minus 5,000 x squared. $2,500 x squared. Oh, yes, you're right. Plus 2,500 x squared. And so this is minus 2,500. And you can see in these problems where the benefit is of doing those derivative checks, because there's, a million places you can make mistakes. But dmdx is equal to 833.3 x squared minus 5,000x. So dmdx is equal to v. We already saw that negative dv dx is equal to q, so they work. I did not explain it. I'd have to think about that. I don't know off the top of my head why. EM. Yeah. Oh, yeah. Right. Yeah, I'll think about it and I'll. Yeah. And then, are we going to plot this? Nope. Hell no. On assignments, you have to plot it, but you can do it on Excel or whatever plotting program you want to use. On tests, I'll never make you plot it. And I think I might have mentioned this before, but So you know that dm dx is equal to v. So that gives you the idea, well, why don't I just start with this v value and integrate it, and then I don't have to go through all this messy rotational Newton's second law stuff to get m. And there's nothing wrong with that thinking. The only problem is that when you integrate v, you have a constant of integration. And so you need a way to calculate that constant integration. And, you know, it's not too horrible to figure out ways to calculate it, but it doesn't end up saving you any effort, really. You might as well just do it this way. And then you can do the checks at the end.
In this case, there's no constant integration, correct?
In this case,
The constant integration is 0.
That's right. Exactly. Yep.
Is that the case a lot of the time?
I suppose that is probably the
Maybe every
case
time?
when you have, that is the case when you have no couples at the endpoint. Or when you have no point couple at the left endpoint, I suppose that's when you have no constant of integration. So yeah, I suppose you could say, as long as you don't have a fixed point or a point couple at the left end, you could just integrate up from v and it'll give you that answer, and you don't have to worry about the constant of integration. I think that's probably true. Any other questions about this? All right. So the next thing I want to talk about, the last thing having to do with internal loads, is internal loads and structures.
So when you put this here,
Yeah.
Well,
it's a way to, it lets you know how likely the thing is to break at those different X locations. You know, so if you're trying to figure out where you need to beef up the material in this beam or thicken the walls or something like that, you want to do it at the X value where those internal loads have big absolute values. Big internal loads corresponds to danger of fracture. They might not, but usually in the problems that we'll see, one or two of them don't really do anything interesting, and the other one does. In most of the problems that we'll do, T and V are pretty much steady, and then M actually has a maximum or a minimum. Okay, so internal loads and structures. If you're given a structure, so let's say this is the structure. With a pin connecting them. And let's say there's a force F applied here. The external loads look something like this. So the external loads on each member look like if this is body 1 and this is body 2, a free body diagram of member 1 looks something like this. You have a force vector RA. You have a point force F. And up here you have a force F12. And the free body diagram of 2 looks something like this. We have a force vector RC, and then up here a force vector negative F12. What is it that keeps us from doing internal loads calculations with these 2 beams? No, that would be fine. We've done internal loads with things with no couples on the end. Yeah. The answer is the relationship between the coordinate system that we're using and the beam. Our x-axis doesn't point along the beam's axis. Okay? So we have a coordinate system when we do this structure calculation, something like this. And that x-axis doesn't point along either one of those 2 beams. Rotation matrices work really well for fixing that problem. So multiply each external load by a rotation matrix that puts the x-axis along the beam. In the example above, for member 1, there's the member. Our original coordinate system is like this. The coordinate system we want, well, there are always 2 possibilities, but I usually use the one that does the smallest rotation. We want, if my thumb is the x-axis, we just want the x-axis to point like that. Okay. So we want a rotation matrix that goes from this to this. In this case, if those angles, well, let me put some angles on these things. Let's say this is equilateral, so these are all 60 degrees. Then what's the angle that you have to rotate the coordinate system to go from our original one to the new one? Yeah, just positive 60. And member 2, looks like this. Our original coordinate system is that. Let's say we want to change it to this coordinate system. So what's the rotation that we need here? I think that, yeah, negative 60, right? Yes. Negative 60 degrees. So then your rotation matrix is just equal to cosine of that angle, sine of that angle, negative sine of that angle, cosine of that angle. And you just multiply this matrix to each of the forces, the external loads on the body. I guess I'll do an example next time. Here's the important thing to remember. We're rotating the coordinate system. Not the member. So look back at these two patients. If you didn't think of it as going from this coordinate system to this one, instead you thought of taking the member and flattening it down horizontal, you would get that angle backwards. That would look like an angle of negative 60 degrees. Same thing here. If you thought of this as trying to tip it up to be horizontal, you'd think this was positive 60 degrees. So you always have to think of the coordinate system. Then once you've rotated that coordinate system, what does it take? Okay, so once you have, let's say, your member like that and your coordinate system like that, what does it take to go to what we're used to calculating, the horizontal member with the coordinate system like this? So, we always do our internal loads calculations like this, right? After we've used the rotation matrix, we're like this. And this is a stupid question. Yeah, exactly. It's nothing. The only thing that matters is the relationship between the coordinate system and the member. So what does it take to go from this to this? Just turn your head a little, and then it looks like that. So once you get here, then you can just draw it like that, So don't think of it as trying to flatten down the member. Think of it as rotating the coordinate system, and then you can draw them however you want.
If you get done, and say you want to put your answers back into your original coordinate system, if it's like a piece of something bigger, can you just divide each force by the rotation matrix, or how does that work?
You would just multiply it by a rotation matrix that goes back again.
Oh, the other, okay.
Yeah, so just the opposite sign.
Would it work to divide it by the one you originally used?
There's no such thing as dividing by matrices. There's multiplying by the inverse, which actually in this case is what you're doing. I mean, so in a way, yes. Because in fact, yeah. Any questions about this?
So basically, once you align coordinate system with your member, you can
Then draw it the way you want it. Yeah. Yep, that's right. Yep. Mm-hmm. If you're using, I think in the programs for statics, I just have it as a 2x2 matrix. But since your program and your calculator is a 3x3, then yes, you have to do it about the third axis, the z-axis. Yeah, so just set your z-axis of everything to be 0. Okay, so at the start of next time, I'll do some example problems.